Okay, so now we're still talking about the Knudsen diffusion, and here we will see the equation that we can use to calculate the Knudsen diffusion. So the equation that we are using is the kinetic theory of gases equation that we used before, or the equation that's derived from the kinetic theory of gases, which was stated that lambda multiplied by u over 3 equals the diffusion coefficient. This is the equation that we mentioned in the very first time we discussed the equations that describe the diffusion in gas phase. So this is the first one. And we had an expression for lambda and expression for u, and u is this square root. But here in this case, lambda is it's the mean free path of the gas molecule. So in this case, since if we are discussing a pure Knudsen diffusion, then the free path is going to be the diameter of the pore. So we are gonna replace lambda by the pore diameter, and then the equation will look like this. You will see that there are a lot of constants here. So 8 is a constant, the kappa Boltzmann constant, n is Avogadro's number, which is constant, pi is a constant, 3 is a constant. So the variables that we have here are the pore, T, and molecular weight of A. So the equation would be very simple like this. So it's this constant multiplied by pore diameter multiplied by the square root of T over Ma. So this is the equation that we can use to calculate the pore diameter in case of pure Knudsen diffusion. Of course, the diffusion coefficient or the diffusion regime or mechanism that takes place is going to be a combination of both. So this is something that we will discuss shortly. But before we go to this, we need to understand or get some information from what we have here in this equation. So we see that the diffusion coefficient is directly proportional to the square root of T. We don't see any dependence on pressure. There is no dependence on the other species that the diffusion is taking place through. And this is one thing that we can see from this comparison, that for the binary gas diffusivity or the pure molecular diffusivity, diffusion coefficient was directly proportional to temperature power 1.5. Here it's only directly proportional to temperature power 0.5. It is inversely proportional with P here, but it's not dependent on P. It's not dependent on the other species, while it is in the case of binary gas diffusivity. So back to the diffusion coefficient versus the molecular diffusion. So again, when we said that we have Knudsen number, so it's not a clear cut between pure Knudsen diffusion and pure molecular diffusion. It gives us an indication of which is more important, and usually you will have a combination of both, or contribution of both diffusion coefficients in the effective diffusion coefficient. And that's why we have what we call here the effective diffusion of A in gas mixture of A and B, which we call DAE. So this is going to be function of DAB, which is the pure molecular diffusion, and the DKA, which is the Knudsen diffusion. We have just seen how we can calculate the Knudsen diffusion, and we have already spent a lot of time discussing the equations that we can use to calculate the binary diffusion coefficients. So if you know both of them, and we know how to calculate them now, and we know the alpha and YA, then we can calculate the effective diffusion coefficient. But first, what is alpha? Alpha is a parameter that depends on the fluxes of the two species. So A and B are diffusing together, and I know the flux of A and the flux of B. There are many cases where the flux can be equal but in opposite direction. So let's say I have a species that is diffusing into the catalyst pore, or in the catalyst pore going to the active side. The reaction takes place and the product is going back the other way. So A is going this way, B is going this way. We can say that in some cases that the fluxes are equal in the magnitude, but they're opposite in direction. So NA equals negative NB in this case. So if NB and NA are equal but in opposite directions, then alpha is going to be 1 minus 1. It's going to be 0. So this term would be 0. Or in other cases where Y is a very small number. So if I have a very diluted mixture, then I can assume that the 1 over DAE equals 1 over DAB plus 1 over DKA. And this is the equation that we will use, because this parameter alpha is not easy to calculate. It's not easy to know where what is the flux of A and the flux of B in a very small pore. So this is going to be easier and more convenient to use the equation assuming that it is 1 minus 0. The last thing that we will discuss here is related to the assumption that we made in the very beginning, which is related to the shape of the pore. So here we assume that the pore is perfect cylinder, but in reality this is not what happens. Usually it is a random irregular pores. So in this case we cannot assume, or the assumption of the cylinder is going to be non-realistic assumption. So we can take care of this by introducing the term epsilon, which is the porosity of the solid phase, and we can calculate the actual effective diffusivity, which is the effective diffusivity multiplied by epsilon squared. Epsilon is the void fraction, or the porosity, which represents how much space is it in the solid material. So epsilon is the volume occupied by the pores divided by the total volume, which is the volume of solid plus the volume of the pores. So this is the summary of all what we mentioned for the cases in the or for diffusion in solid phase. So we have here the case of pure molecular diffusion when lambda is very small compared to the pore diameter. We have the case of pure molecular, and in this case we use the equations like Hirschfelder's equation. For pure Knudsen diffusion, we use the Knudsen equation, and we have already seen if we group all the constants, then the equation would be simpler than this. And the case of Knudsen plus molecular diffusion, where we calculate the effective diffusion coefficient from the molecular diffusion and the Knudsen diffusion. And finally, the random or the diffusion in random porous material, where there are like tortuosity in the solid material, and in this case the diffusion coefficient, which is the actual diffusion coefficient, equals epsilon squared multiplied by the effective diffusion coefficient that we calculated from here. The last thing we'll do is to solve an example, and in this example we have a mixture of carbon dioxide and ethylene gas. They are diffusing in a random porous material. We know its void fraction and the total system pressure and temperature, and we need to estimate the effective diffusion coefficient of carbon dioxide and ethylene within the pores, the porous material, if the mean pore diameter is 0.2 micrometer. So from the statement of the problem, we can say that we know the carbon dioxide and its molecular weight, we know ethylene and its molecular weight, we know the porosity, we know the temperature, we know the pressure, we know the pore diameter. It is here in meter. It's 0.2 multiplied by 10 to the minus 6 because it's a micron, so to convert it into meter we multiply by 10 to the minus 6. So this is a summary of all the information that we need or we know. So the calculations would be very simple. I just follow the equations that we know. So I'm gonna start it from the end to the beginning. So I want to calculate DAE dash, which is equal to epsilon squared multiplied by DAE, and I know that DAE equals this equation, DAB multiplied by DKA divided by the summation of 2. So if I know these two and I already know epsilon, then I'm done. So what I'm gonna do is calculate the molecular diffusivity and the Knudsen diffusivity. So Knudsen diffusivity is gonna be very simple. I know the pore diameter, I know the temperature, I know molecular weight. I put the pore diameter here in centimeters, so that this is centimeter squared per second. So I know the Knudsen diffusion. And I can estimate the DAB, which is the molecular diffusion, using the Hirschfelder's equation. Again, we have already discussed this a lot before, so I'm not going to go into the details. It's going to be just getting the parameters that I need to get the value of diffusion coefficient. So I know sigma A and sigma B from tables, and then I can get sigma A B. I know epsilon A over K and epsilon B over kappa. I'm sorry, and then I can get epsilon A B over kappa, which is gonna be this value, and from epsilon over K I can get the dimensionless temperature, which is kappa T over epsilon, and from the chart or from the table I can get the omega D, and by substitution I can get the value of diffusion coefficient, which is 0.077 centimeters squared per second. And from here you can see that this diffusion coefficient is much smaller than this. So the diffusion due to the molecular diffusivity is much smaller than the Knudsen diffusivity. These are the values that I know, and then I can get the effective diffusion coefficient. This is one thing that is worth like a 1 minute of discussion. So you would see that the diffusion coefficient here is, its value is very close to the value of the DAB, which is the smallest one. So it seems that it's controlled by the molecular diffusion than it is by the Knudsen diffusion. And from this equation, you can tell that the value of DAE will be smaller than the smallest of these two. So this is something that we see in mass transfer. You would see, and it's gonna be clearer if I go back to to this equation. So this equation mathematically tells us that this is gonna be smaller than the smallest of these two. You can try any numbers, it's gonna be always smaller. And this is what we see in heat exchangers, for instance, when you say 1 over U equals 1 over HI plus 1 over HIO, this U is always smaller than the smallest of both. So this is something that we see a lot. So this is something you can expect, and this is something that you can predict from the beginning. Back here, so this is the effective diffusivity. One thing that we can do as a quick check is to see the Knudsen number. What is the value of Knudsen number? So Knudsen number, we can calculate lambda first from the kinetic theory equation. Again, you can go back to the beginning of the gas phase part, and then this is the shape of the equation that we had, and this is the value of lambda, and from this you can calculate Knudsen number, which is 0.168. So it's very small. It's not very small, but it's very small compared to 1. It means that the pore diameter, or the lambda, is 16% of the pore diameter, which means that the pore is very big compared to the pore, the mean free path. And so it makes sense that the effective diffusion coefficient is close to the molecular diffusion. So this is something that I wanted to highlight. Finally, the actual effective diffusion coefficient is going to be 0.0122 centimeters squared per second. One last thing I want to mention in this equation, or in this problem, which is something that is noteworthy actually, which are these graphs. So this graph is already in the textbook. You can check it in the solution. So it tells us how the Knudsen number changes with the pressure. So we know that at high pressure the mean free path is small, and at low pressure the mean free path is big. So this is what this graph tells us. So at very small pressures, you'd see Knudsen number here is almost 3 point something. Which means that the Knudsen diffusion is very important in this case. But as the pressure increases, you'd see that the mean free path is decreasing rapidly. So going just for a little bit of increasing pressure, the Knudsen number is almost 1, and with a little bit, we're still under or below 1 atmosphere, so it's decreasing rapidly. And at high pressures, the Knudsen number is 0.0 something, which means that it is it's almost not effective. And this is what we can see from here, from the effective diffusion or the diffusivities. We have here the molecular diffusion, Knudsen diffusion, and effective diffusion. Knudsen diffusion is not affected by the pressure by any means. So no matter what the pressure is, the Knudsen diffusivity is constant. And this is what we mentioned when we discussed the Knudsen diffusivity. But you'd see at very low pressures, when the Knudsen number is very big, you'd see that the effective diffusion coefficient, which is this, is almost equal to the Knudsen diffusion. Okay, but as the temperature or the pressure increases, then the distance between the Knudsen diffusion and the molecular diffusion, the effective diffusion and the molecular diffusion, gets smaller. And at very high pressures, the Knudsen diffusion is almost not effective. It's also nice to notice that always the effective diffusion coefficient is below or lower than or smaller than the molecular diffusion and the Knudsen diffusion. It's never larger than them. So this is also a nice thing to notice. Finally, here you would see that the effective diffusivity or the ratio of the effective diffusivity to the molecular diffusivity. So again, at very low pressures, there is a very big difference, a very big difference in the values between the effective and the molecular diffusivity. So it's less than 20% of the molecular diffusivity. But as the pressure increases from 0 to 2 atmospheres, you would see that it's almost 80% of the molecular diffusivity. And as you increase the pressure more, it's getting more and more closer until it's going to be almost pure molecular diffusivity. So these are nice graphs that tells us a lot about what we mentioned in the equations that we described before. And by this we end chapter 22, and the next video we're gonna start the next chapter, which is chapter 23. So I'll see you then, inshallah. Goodbye.